All right, so our next speaker today is Daniel George. He's at Macquarie University, and he's going to talk about entanglement in quantum field theory via wavelet representation. So Dan, the floor is yours.
Great, thanks, Eduardo. So this is essentially just reviewing some recent results that we published last month. It's a collaboration between a number of people, as you can see there, internationally. Yuval and Gavin are both based in Sydney. Gavin is my supervisor, and Mohsen and Barry are both Canadian. You can see the DOI there and the archive link if you're interested in looking up the rest of the paper. So we were studying, the title is Entanglement in Quantum Field Theory via Wavelet Representations. We were looking at a number of features of quantum field theory using a wavelet basis. So what is a wavelet basis or a wavelet transform? It's a way of it's a technique taken from the signal processing literature. It allows you to break up a signal to look at features at different scales fundamentally. So this here is an image of Sydney that I've processed using a two-dimensional wavelet transform. You can see how the features, you've got very coarse grained features, very in the top left of the right side here. I don't know if you can see my mouse. In the top left, and then additional layers or wavelets, wavelet representations will then add refinement to that coarse grain representation. You can also see in particular that at least in the case of this two-dimensional wavelet transform, that the direction of the features is also significant, although in our case we mostly looked at one-dimensional transforms. So the wavelet basis consists of those scaling and wavelet functions that are defined recursively. The scaling functions are defined recursively in terms of themselves, multiplied by these wavelet coefficients Hj, and scaled dyadically and translated. The wavelet functions are also defined recursively in terms of scale functions. However, there's a differencing that goes on such that the scale function effectively forms a kind of block averaging or a low pass filter, and the wavelet function provides a block differencing or a high pass filter. Now we used the Daubechies DBK wavelet family. This is defined as the unique minimal order set of wavelet coefficients such that the first K moments vanish. And the reason we like these is because they have particularly nice orthonormality properties, which simplifies the calculations quite a lot. And curiously, except for the very basic case of K equals 1, there's no closed form expression for them. They're only, it's a result of the recursive definition. However, we can still do those recursive calculations, get approximations. So here's the first 6 Daubechies wavelet families. You can see for K equals 1, you've got the familiar Haar wavelets, where you've got the scaling function and the wavelet function in orange and purple respectively. And then as you go increase the index K, the wavelets get smoother. And the increased vanishing moments result in a smoother wavelet that is additionally differentiable. So from, for example, K equals 3 upwards, the wavelets are actually smoothly first differentiable and then second differentiable from further up and so on. So the wavelet basis is a countable basis for square-integrable functions in L squared on L2 on R, the real functions over the real 9. You can take the scaling functions at any scale, which we describe as 0. Sorry, there's an echo. Which is essentially arbitrary, and then wavelet functions at successively finer scales will then provide that refinement, which is kind of represented here at the bottom. So the wavelet transform is also an exact holographic mapping, and where the bulk and the boundary contain identical information. This allows us to speak of a bulk and a boundary picture using the wavelet transform. And part of what interested us was what can we say about the geometry of the bulk using these Daubechies wavelets, which will come up in a bit. Oh yes, and then just quickly, this is what happens when you do that wavelet transform while increasing that wavelet index k. You can see that there's a sense in which the image becomes smoother and more detailed to a point, even though there's no actual additional resolution. Okay, so I've shoved all the equations onto 2 slides here that just sort of describe the systems that we were dealing with. So this is the Fermionic Hamiltonian that we used for our fermionic calculations. It's the free-Ising model and the Majorana spinor formulation given there, the anti-commutator as well. Note the continuum massless phase correlator here has this 1/x dependence in the large separation limit. And then this is what the Hamiltonian looks like after it's been discretized in the wavelet basis. So once you take this overlap with the scale functions in the individual Majorana modes, you get these Majorana scale functions, which are then connected by this coupling matrix Q. Derivatives are replaced by these deltas, which are derivative overlap coefficients. Somewhat unexpectedly, these are rational. And you can calculate those, but just based on the properties of the wavelet family. The Bosonic Hamiltonian is the free scalar Bosonic model. Commutators is given, and then you've got the classic massless phase correlators and massive phase correlators here with polynomial decay and exponential decay, respectively. And the massless phase, you've got these long-range correlations that we'll show up later. The discrete Bosonic Hamiltonian, once you've put it into the wavelet basis analogously using that overlap procedure, also you've got this expression for the coupling matrix in terms of these derivative overlap coefficients. So we started by essentially doing a numerical calculation of the correlators. We're interested in the behavior of the same scale correlators, so within the bulk, looking at different positions but the same scale, and the why will become clear in a bit, but at least in part it's because you can also show that the cross-scale correlators in all cases will decay exponentially just as a consequence of the way the transform works and the negative curvature of the space. And this is an example showing how the coupling matrix and the ground state covariance matrix transform under the wavelet transform, where instead of just having near neighbor coupling, you've also got coupling between scales. Sorry, excuse me. All right, so the fermionic correlators are shown here, where for the critical phase, we got a really nice fit to the analytic expression given here with the polynomial decay with an exponent linear, polynomial decay with an exponent linear in K, the Daubechies index. The analytic calculation for the massive phase was a little bit more complex. But what we've got here is we've done a least squares fit, assuming a 2 to the n minus r dependence on the mass. So this m tilde here is a renormalized mass. And one of the really nice things here is that the mass renormalization just pops straight out of the wavelet basis without any kind of fine tuning required. This is the Bosonic correlators, which show polynomial decay and exponent proportional to the Daubechies index. And in the massive case, you've got, again, the scale-dependent mass renormalization with the m tilde with a dependence on the 2 to the r minus n. Now, the mutual information, the reason why we're interested in the correlators is essentially because we can connect that to the mutual information like so. So the correlators, the expressions for the correlators were used in these calculations with the mutual information. And then the mutual information, it can be shown, sorry, I'm going to move reasonably quickly through this part to move on to the next section. You can actually, by assuming, say that again?
2 minutes.
No problem. Assuming the mutual information taking this form, you can actually show that there's a dependence, a connection between the radius of curvature of the bulk geometry and the choice of Daubechies index k, which for large k becomes linear. So that's really nice. It means you've got this exact holographic mapping with a tunable bulk geometry. And then in the remainder of the 2 minutes, I'll just talk about the holographic subsystem, entropy, and here the entanglement wedge. So the entanglement wedge is a geometric quantity when you've got two subsystems on the boundary that are then let's get back here. The subsystem entanglement entropy, or the combined entropy, is equal to the length of the geodesics joining the boundary points of both these two subregions. Once the geodesics join the boundaries of the subregions, you've got this connect here, which occurs at some critical value d over L greater than √2 minus 1. And this is the entanglement wedge. Now, the entanglement wedge is conjectured to be equal to the entanglement of purification, which is a very difficult quantity to calculate. I'm going to skip over the exact details of how that's done. But we were interested in whether or not we can make that easier by coarse graining on a wavelet basis. And also whether we can identify that phase transition that occurs when the geodesics switch from joining the boundaries of each individual region A and B to joining between the boundaries of the regions A and B. And we found that you could, so that there is a peak in this value X, which occurs specifically when you've got a single coarse-grained mode. The details of this are in the paper if you're interested. And so that was great. We also showed that you can use the wavelet transform to identify quantum phase transitions for a fermionic system using a overlap, essentially calculating or approximating overlap fidelity using a coarse-grained state. So wavelets provide an especially convenient basis for describing multi-scale properties of quantum field theories. In particular, renormalization is readily apparent and just comes out without any fine-tuning. And the wavelet index, in the case of Daubechies wavelets, allows tuning the bulk geometry and the holographic picture. We can also do wavelet compression, where coarse graining to a couple of coarse modes allows for a calculation or approximation of certain values and for identification of phase transitions. And then you can see there that I've listed a couple of future directions for our research. Thank you very much.
Thank you very much, Dan. Thank you. And same as Joshua, a special thanks because it's very late there where you are. Right, we have time for one quick question. Please put your hand up. If not, we can also have the questions, if you can make it, of course, in the after the session finishes. If not, we can also use.
Probably not, but if people put questions in the Slack, I'm very happy to answer them tomorrow and the next day as I get a chance. So
wonderful.
Great.
Well, thank you very much, Dan. Thank you.